let's take a look at kinetic versus thermodynamic control. And when Klein talks about kinetic control, he's usually talking about 0 degrees Celsius or some kind of lower temperature. And when he's talking about thermodynamic control, he's usually talking about 40 degrees Celsius and above. So we know that when we're talking about kinetic products, the 1, 2 adducts are going to dominate. And when we're talking about thermodynamic control, the 1, 4 adduct is going to dominate. And the reason for this, we went over this in class, but the reason the 1, 2 adduct predominates at low temperature is due to the proximity of the proton and the group that's added to it, the anion. And when we're dealing with higher temperature, the reason the 1, 4 adduct is the preferred product is due to stability, because it gives you a more substituted alkene. Stability. Okay, so let's take a look at this first example here. If we have hydrochloric acid in this diene, so I'll draw in all my electrons here, there's only 2 places that we can protonate this molecule, and they're both going to be identical. Whether you do it on this carbon or on this carbon, you're going to end up with the same product. So if we protonate here, what we're going to end up with is we're going to have a cation right here, and here is our double bond. And what's interesting about when we protonate these kinds of molecules like this, oh, I should erase this mess that I'm making. When we protonate molecules like this, is that you see is that the carbocation that's formed is stabilized by resonance. So if I draw the other resonance contributor, it's going to be the more stable of the 2 alkenes, and our cation is going to be up here. But even though this is the more stable of the 2 carbocations, we know that since this reaction is done at 0 degrees Celsius, our 1, 2 adduct is going to be the preferred one. So we're going to proceed through this intermediate here due to the proximity, because if things are cold, things aren't moving very quickly, so it's going to seek to finish the reaction as quickly as possible. So we already added a proton here, and now, and I'll switch to a different color here, switch back to black. So if we have our bromide, it is going to react at our carbocation to give us our product. So here's our product with our bromo, like this. And I'd like to point out that this product is going to be racemic, because this could attack from either face of the carbocation. So this is racemic, a racemic product. And you might see some of this product as well, but it's going to be formed in a much lesser extent. So again, if we have our bromide here in solution, it's going to attack at that carbocation, and we'll end up with something like this. And this is the more stable of the 2 products, but this is not going to be the major product because it is formed at, or the reaction is performed at 0 degrees Celsius. So this will be our major product here. This product formed in a racemic mixture. So if we go down to this next problem here, again, this reaction is being done at 0 degrees Celsius, so you would expect the kinetic product, which is the 1, 2 adduct. 1, 2 adduct. So again, if we draw, let me just move this down a tad. If we draw an HBr here, there's all my electrons. So if we protonate here, then our product is going to look something like this, where we protonate there, draw my 5-membered ring, and my carbocation is going to be here. And you can see again that this carbocation is going to be stabilized by resonance. So if we draw the other resonance contributor, it's going to be the more substituted alkene, like that. And now our positive charge will be down here. But since the reaction is, again, being performed at 0 degrees Celsius, we know that the 1, 2 adduct is going to be the product that's going to dominate. So if we just draw our bromide here, again, we draw our electrons going all the way up here to this carbon here. You can see that the 1, 2 product will look something like this, where we have our bromide here. And this can attack from either face of the molecule as well. So this is going to be a racemic product. And the 1, 4 adduct would be this product here, where we have the more substituted alkene, but this product is not the major product because this reaction is done at a low temperature, 0 degrees Celsius. So again, this would be formed in a racemic mixture. But since the reaction, again, as I've repeated several times, has been performed at 0 degrees Celsius, we know that the kinetic product, the 1, 2 adduct, is going to be the preferred product. So let's take a look at this last question here. It said, okay, well, if we have the same molecule that we had above, so we have the same molecule here, but now we're doing the reaction at 40 degrees Celsius. Well, hopefully you would know, based on what we just talked about, that the preferred product would be the 1,4-adduct that we see over here. So it all depends on the temperature. If the temperature is high, we're going to get the more stable alkene. So you can see this is the more highly substituted alkene, which gives us the more stable product. And if the reaction is performed at low temperature, then we're going to get the 1,2-adduct, and this is because of the proximity of the two things that are being added to our diene.